Welcome everyone. My name is Vladimir Pane. I'm the field application engineer for variable frequency drives. I've been working for Delta for over 6 years, and I'll go very quickly through what is a variable frequency drive. I've looked through the attendees list, and I see most of you already have quite a lot of experience with drives, so I won't stay too long on the basic topics. So what is a drive? What is an AC motor? And how do drives work? I will focus a bit more on some common functions for variable frequency drives. I'll give you just a very rough overview of the Delta drives. And I will focus also a bit on how to select drives for different applications, what are the selection characteristics. And then finally, we'll have a bench demo, which will be followed by a Q&A session. For more information on Delta's products, you can visit our YouTube channel. This is called Delta Industrial Automation EMEA. You can also visit our download center to get the latest manuals, catalogs, drawings, and EDS, GSD, GSDML files, and all of that. I put here just a quick graph to show you the different drives that Delta has released in the last 25 years. And drives are widely used across many industries, and it's always good to have the right product for the right application. So very quickly, what is a frequency drive? There's many names which you'll find on the market, like variable frequency drives, variable speed drives, inverters, AC motor drives, variable voltage, variable frequency drives. So that's VVVF. I think that's mostly used in Germany, and others. And most of the times they all refer to the same device. So there are over 100 different functions in a drive, but the fundamental one for which we call them variable frequency drives is the fact that they take the fixed characteristics of the electrical grid and then they convert them into controllable units. So they take the fixed voltage and the fixed frequency and they convert them into variable voltage and variable frequency. So why would you like to do that? Why would you control the frequency? Well, that's because the speed of a motor is dependent on the frequency that you supply it with. So the types of motors that we can control with our drives can be induction or asynchronous motors, permanent magnet motors, or more recently, synchronous reluctance motors. Most of the times they're made out of a fixed part called stator and a moving part called rotor. If you look at the cross section, you can see that the motor is actually made out of thin laminations separated by all insulated each other and stacked upon another. So that's to minimize eddy currents and other such effects. You can see here a complete list of all the components of a typical motor. And both PM and IM motors, so that's both permanent magnet and induction motors, work on the principle of the rotating magnetic field. So that means that the stator generates a magnetic field which pushes the rotor in a rotary movement. The speed of the rotor is proportional to the frequency that is supplied with, so a higher frequency will result in a higher speed. Now, the torque that is being developed by the motor is proportional with the current that is going through it. So in most cases, if you have a higher torque applied to the motor, then you will see a higher current. So how does a variable frequency drive work? There are some major components in the drive, especially in the power electronics of it. So you have the rectifier, the DC part, and the inverter side. This is one of the reasons why I generally don't prefer to refer to drives as inverters, because inverter is normally just one part of the drive. So it's not totally correct to refer to the whole drive as an inverter. But okay, so you have the rectifier on the input, and this converts the fixed main supply voltage it converts it from AC to DC. And then the DC voltage is then converted into a controllable AC voltage with the help of the inverter. So this is a three-phase rectifier. A single-phase rectifier will have two diodes less. Regardless of whether the input of the drive is three-phase or single-phase, this will be converted to DC, so that's plus and minus. The output will always be three-phase. We do not make drives for single-phase motors. The way that the inverter converts the DC voltage into AC is by using the IGBTs. So these have the ability to open and close very fast in the order of kilohertz. And they help to simulate a sort of AC voltage that's called pulse width modulated, PWM. So they simulate that AC voltage by chopping the DC bus voltage into thousands of small pulses, which you can see here on the right-hand side. The sequence with which the IGBTs will open will determine the output frequency, so that's the fundamental frequency. But the duration at which they open will determine the voltage, the root mean square value of the voltage. So the pulses will still have the amplitude of the DC bus voltage, but the root mean square will be depending on the duty cycle, so on how long the IGBTs stay open. So with drives, we always talk about two frequencies. One is the fundamental frequency, which you can see here, and that is what determines the motor speed. So it's this one drawn in a continuous line. And the fundamental frequency can be anywhere from 0 to 600 Hertz for low-speed drives, or up to 2000 Hertz for high-speed drives. So for some models like the MS300 and C200 and a few others, you will have to choose between a low-speed drive or a high-speed drive. Another frequency that we refer to is the carrier frequency, sometimes also called the switching frequency. This is the frequency which helps build the fundamental frequency. And this is normally somewhere between 2 kilohertz to 15 kilohertz. In order for the fundamental frequency to have a somewhat acceptable form or shape, there needs to be a minimum ratio of 1 to 10 between the fundamental frequency and the carrier frequency. So if you're working on a high-speed application, on a motor which requires an output frequency of around 600 Hertz, then you need to make sure that the carrier frequency is at least 10 times higher than that. So you need to make sure that you set the carrier frequency to at least 6 kilohertz. If there are no questions, then we'll move on to some typical drive functions. These are some of the most common functions that are used with drives. Almost all of the functions that I will mention are supported on all of the Delta drives. If there is any particular function that you would like more information, then please feel free to raise your hand and ask. So I'll start firstly with the PID control. And this is normally used to control dynamic processes such as flow, temperature, pressure level, and other. You normally have a feedback sensor that can be 4 to 20 milliamps, 0 to 20 milliamps, 0 to 10 volts, and other. And in these applications, you don't actually care about the speed at which the motor is running. So if, for example, you are trying to achieve a pressure of 6 bars, then all you really care is that your pump will increase the speed when the actual pressure is below 6 bars and decrease the speed when it's above. Another very common function is skip frequency, and this is also related to the previous function that I mentioned. In many applications, you get a mechanical resonance when the motor runs continuously at a particular speed. The drive can help prevent that by making sure to never run continuously at the frequency at which this resonance occurs. So you have different parameters in the drive in which you can set the areas which the drive will avoid. So this function can be combined with the previously mentioned PID function. So this doesn't mean that the drive will just jump from one frequency to another. Rather, it will not allow the drive to run continuously in this range. So if you program, for instance, 128 to 35 Hertz and 129 to 30 Hertz, if you are ramping up and the set point is set to 33 Hertz, then the drive will just remain at the setting from 129. It will just remain at 30 Hertz. If the set point moves to 35 or 36, then the drive will ramp up through 31, 32, 33, and so on until it reaches the set point. So the only difference is that it will not stop in that area.
We have a question from Sebastian. Sebastine, do we have a feature to reverse the ramp direction under analog control?
I think you mean that you want to have you want to control the direction of the motor. So you don't want to give the drive a reverse command and a forward command. You want to do it just with the analog input. So for instance, if you give it minus 10 volts, then it runs reverse. And then when you give it plus 10 volts, then it runs forward or something like that. If I understand your question correctly, that is possible. And even if you are using a drive which doesn't have a minus 10 volt terminal, you can still do it with 0 to 10 volts. You just have to set the middle point. So for instance, the 0 Hertz can be 5 volts. And then if your command is below 5 volts, then it can run reverse. If it's above 5 volts, then it can run forward. And I just mentioned now for an analog input of 0 to 10 volts, but you can also do it if your input is 4 to 20 milliamps. So that would work in a similar manner. If your command is somewhere at 12 milliamps, then that can be 0 Hertz. And then when it's below 12 milliamps, then it can increase the speed in the negative direction, in the reverse direction. And when it's above 12 milliamps, it can run in forward direction. So I hope this answers your question. If not, please type underneath and we will check it out. Okay, so moving forward. Next, we have the overvoltage stall prevention. Now, this is commonly used in applications which have a lot of inertia. So sometimes you have some centrifugal fans, which might take a few minutes to stop when they are running at full speed. And you want the drive to control their stop. You want the drive to be able to stop them properly, but you do not want to wait for a couple of minutes before that happens. So what the drive can do is it can start to decelerate. It can start to lower the output frequency, and then it can detect that the DC bus voltage is raising to a higher level, and then the drive will stop from decelerating. So it will just run a straight line. And then when the DC bus voltage is increasing again, then the drive can again stop from decelerating. So this is called the overvoltage stall prevention. And you normally use this when you don't want to use a braking resistor. So this could be achieved very easily by using a braking resistor, but in many applications that's not really wanted. So so you can also use this function. The only difference is that the drive will then no longer stop in the time that it's programmed, but it will take a bit longer to stop, as you can see here. Next, there is the overcurrent stall prevention. And this works in a similar manner to the overvoltage stall prevention. The difference is that this time the drive is looking at the output current. So let's say you are running a fan for some applications or some pumps. And especially for these applications which have a variable torque, if you decrease the frequency by just a bit, then you will also see the current decreasing on the motor. So that's something which some applications need and use. So you can see here that you can program this in parameter 604, and the drive can detect this. If the output current is above the level that you programmed, then the drive can automatically decrease the output frequency until the output current drops below a certain value, until it drops below 6.04. Then it can increase back to the previous setting. A commonly used function, especially in applications which have very high inertia and which take a very long time to stop, is the flying catch function. So we also call it speed search. If you look through our manuals, then you'll find it under this name. So as mentioned before, some fans might take a number of minutes to stop, sometimes 5 or even 10 minutes to come to a complete stop. If you try to run a motor, if you try to run one of these fans while it's turning, then that's gonna draw a lot of current, and the drive will just trip on overcurrent if you do not use the speed search or flying catch function. So what you can see, for instance, in this graph is the output frequency in the red line, and you can see the DC bus voltage in the green line. And you can see that there is a power dip here. You can see it based on the DC bus voltage, which is decreasing here, but then it comes back. So that can happen very often on a network, that you have a power dip for a few seconds, which then comes back. So it's not something that you want to do. You don't want to wait for 5 minutes or 10 minutes until the fan comes to a complete stop so that you can run it again. So what the drive does, it detects that the power is back on, and then it can automatically detect the speed at which the fan is running. So you can see here it was running previously at 35 Hertz. Then there is the power dip. And then after a few seconds, the drive catches the motor, catches the fan at around 25 Hertz. So within these seconds, the speed dropped from 35 to 25 Hertz. The drive correctly catches it at this speed and then ramps it back up to its normal speed. Now, another function that we do use quite successfully is the energy saving. So you can have a look here. You also have the output voltage plotted in this graph, and the output current. So in many applications, if you are not running at full load, so let's say if the application is an escalator, most of the times you'll see escalators running without anyone actually being on them. And so you can use this function to decrease the output voltage. And by decreasing the output voltage, you can see the output current decreasing quite a lot. So even though the escalator will run at the same speed, because the output voltage will be half or even less than that, and then you also have your energy consumption. Of course, the drive will detect if if some load is added to the motor, to the escalator, then the drive will automatically increase the voltage back in order to get the right amount of torque. So moving on to functions which you more typically see in constant torque applications. So very commonly used is the mechanical brake control. So you can program one output of the drive to command that's usually a relay output to command the mechanical brake, which is normally installed on a motor. So you normally have this in crane applications, in winches, in elevators, and other. So you can set certain rules for when the mechanical brake should open. And you normally do this based on the output frequency and the output current. So before you open the mechanical brake, you normally want to make sure that the motor is developing enough torque to actually run the load. So you want to make sure that it's that you don't see any sagging, or you want to see that you want to make sure that the load isn't dropping. So then you can program the output frequency and output current at which the mechanical brake should open, should release. And then you can also program the frequency and current at which the mechanical brake should close, or it should engage. And please note that in order to open this the mechanical brake, in order to open the relay which controls the mechanical brake, you have an AND function between the output frequency and output current. That means that both conditions have to be met in order for the mechanical brake to open. However, to engage the mechanical brake, to close it, you have an OR condition. So that means either that the output frequency drops below your settings, or that the output current drops below the minimum value that you set. So if any of these conditions are met, then the mechanical brake will engage. Another function which is typically used in hoisting applications which are open loop is the DC injection braking. So with this, you can inject a DC current into the motor in order to make sure that there is no movement before you start and stop. So this function is also typically combined with the mechanical brake control that I mentioned earlier. Then you also have dynamic braking. So in many applications in which the load is actually pulling on the motor starts to work as a generator. So instead of having the drive feeding energy into the motor, now it's the motor which is feeding energy back into the drive. But the input of the drive is a diode rectifier, so there is no way for that energy to go back into the main supply. So what usually happens is that all that energy will just go directly onto the drive's capacitors. This means that the DC voltage will increase, and the drive has a protection function to just automatically trip to disconnect from the motor when the DC bus voltage reaches 820 volts. But if the drive disconnects from the motor, then the motor will no longer stop within the programmed amount of time. It will just coast to stop. So it will stop based on its own inertia. So what we normally do is we can connect a braking resistor to the drive. Many of the low power drives have a braking chopper built in. And for higher powers, you can connect an external braking chopper. So the braking chopper is the device which dumps all the energy onto a braking resistor. You can also program S-curves. So these are especially useful in elevator applications, but not only, in order to make sure that you don't have a very rough transition from accelerating to constant speed and vice versa. Almost all of our newer drives come with built-in STO, safe torque off terminals. At the moment, the level of this is SIL2. And finally, all of our drives come with motor protection functions and phase loss detection functions. So phase loss can be either input phase loss or output phase loss. So if you have any questions on these functions, or if you want to have more information on some other functions which I've not presented here, then please let me know, and we can also go over those.
There is one question still about that ramp direction. The question was if I want a pressure of 6 bar, if below it ramps up and if above it ramps down, can I change it and operate it in another way? But normally automatically with a PID and a pressure sensor, it will always go up and down around the 6 bar, what you have as set point.
Yeah, no, that's true. I don't quite understand the statement, can I change it and operate it the other way? Definitely you don't want to run it reverse, I'm sure of that. But yeah, no, if you're running in PID, then the drive does that automatically. So it will just, if you set the pressure to 6 bars and the pressure is actually 5.5 or 5 or something like that, then the drive will automatically increase the frequency up to the rated frequency of the motor. If the pressure is above, then it just decreases the frequency down to a stop until it reaches that set point. And how fast the drive reacts to this depends on the setting, on your PID settings. So it depends on the proportional and on the integral gains that you set. So I hope this is what you are referring to. If not, yeah, please let me know. Okay, so moving on. I'll just give you a quick introduction to how the type numbers are composed in Delta drives. This is the old style of type numbers, which is based on drive power. So you have the VFD for variable frequency drives. You also can have the active front end or regenerative units. But I will not present those in this presentation. So if you want more information on that, then we can discuss them separately. Next, you have the power of the drive. So this can be 007 stands for 0.75 kilowatts. So you can have up to, at the moment, the highest power that we have is 630 kilowatt. Then you have the drive series, followed by voltage. So 4 stands for 400 volt, and 3 stands for 3-phase. Sometimes you'll see it as 4E, and that will be a 400 volt 3-phase drive with built-in EMC filter, but that's only for some particular models from the C family. And next, you have the hardware version. Now, the new type numbers, starting with the M300 series, are based on current. And later on in this presentation, I will let you know why it's better to have this based on current and not based on power. You might think that it's easier, and indeed, in most cases, it is easier to select a drive based on power, because you might think, okay, I have a motor which is 5.5 kilowatt, so I will just take a drive which is 5.5 kilowatt. But actually, you'll see in the next chapter, in the drive selection chapter, that there is many different factors which you need to take into consideration when you select a drive, and just selecting on power can lead to some incorrect selection. So the new drive series, which we released in 2016, has changed the naming rule based on current and added a few more letters. So now you have the current, so 1A6 means 1.6 amps. Then you have the drive series, so that's ME, MS, and in the future we will also have the MH300. The naming rule for voltage is the same. Then you have the IP protection, followed by a filter, so you can have with or without an EMC filter. Then you can select models which don't need safety functions, so you can have without an STO or with built-in safe torque off terminals. You can also select between high-speed models and standard models. So as I mentioned previously in this meeting, standard models will have an output frequency of up to 600 Hertz. and high-speed models can go up to 1,500 or 2,000 Hz, depending on the model. And then finally, you have the hardware version. So I would like to start with the most recently released drive, that is the ME300. This is a compact economy drive. You can see here the standard specifications and features. What sets it apart is that it can run permanent magnet motors in sensorless mode. That's sometimes useful for fan applications where it's important to save energy by using a more efficient motor like a PM motor. You can check here the standard specs. I will go through these very quickly, but if you have any questions on any particular drive series, then feel free to let me know. Since this is the economy drive, there's fewer IOs. There's no possibility to connect an external communication card, and there's no built-in PLC. So this can go up to 7.5 kilowatt or 17 amps. Next off, we have the MS300. This is part of the same family of the ME, but this can go up to 22 kilowatt. This does have a built-in PLC. Later on in this presentation, I'll show you how to connect to that built-in PLC. It has more IOs, more functions, and you can also connect optional cards, which allow the drive to be controlled via different protocols, such as CANopen or Profibus or Ethernet, and so on. You can also have high-speed models with this drive, which can go up to 1,500 Hz. Now, this is one of Delta's most popular drives. I think this is from the previous generation of compact drives. So you might see some features which are not there, which you normally find on the MS, but not on the VFDE. But still, it's a very popular drive. But I will not focus on it too much. And then you also have the EL drive, the micro drive, also from the previous generation of drives. Then I'll move on to the C2000. This is the high performance drive, which does support closed loop field-oriented control. You have a number of functions to control induction motors or permanent magnet motors in positioning mode or in torque mode, and you can also control in sensorless mode synchronous reluctance motors. It does come with a keypad which can save parameters and PLC programs. So you can save them to the keypad and then you can upload them. You can connect the keypad to other drives and then move it to different drive. The keypad also supports user design screens similar to a mini HMI or a text panel, and that can access different addresses in the drive or in the built-in PLC. And later on today, I will show you some functions related to positioning and to synchronization. Then we have the CP2000. You can also check its specifications and its features here on this page. It can go up to 630 kilowatt. This drive, together with the CFP2000, are made for usually fan and pump applications. So if you check the features that they have, you can see they are normally made for this. So they have built-in backnet, built-in fire mode. You can control different motors in cascading operation. If you have any questions on this, then you can let me know. The CFP2000 is very similar in functions to the CP2000 drive. The difference is that it's IP55. So while the firmware is completely identical to the CP2000, there are some significant differences in terms of hardware. So the built-in EMC filter does not stop at 37 kilowatt, but goes all the way up to 90 kilowatt. And also the built-in DC reactor is also present through the whole power range. So in the CP2000, it's only from 45 kilowatt and above, but on the CFP2000, you have a DC reactor also below that. At the moment, it's only 400 volt up to 90 kilowatt. However, we will very soon release the 230 volt and 600 volt models. Finally, the last drive that I would like to show in this presentation is the VFD ED drive. And this is made for elevator applications. So you can find some typical functions for elevators, such as EPS input. So that means that you can connect UPS to the drive for emergency rescue operations. If, for instance, there is a power down in the whole building, then you can still use the drive to detect the direction of the car, to detect which way it's easier to move. And the drive can control that. So the drive can move the cart to the closest floor in order for its passengers to be able to get out. And it also supports typical encoders which you find in elevator applications, such as NDAT and hyperface. And of course, some other typical functions like torque feed forward, which means that if you note a loading on the motor, then when you release the mechanical brake, you can apply a torque feed forward in such a way that there will be a very smooth release. That's about it. There are other drive series, but these are the most popular. So if you want more information on different drives, then you can let me know.
There's one question. Is it possible to control 6 motors with one drive? What are the limitations? It's depending on the drive type, of course. If you look for the CFP or the CP, you can run 8 pumps directly with one drive if you want. But I don't know exactly what the question is in this case, for what drive.
Yeah, I think it depends on the mode that you want to run in. So for some modes, if I remember correctly, you could run up to 4 motors. And with other modes, you could run up to 8 motors.
This is for the MS300, the question. So that's...
No. in that case, well, yeah, this really depends. If you are referring to the multi-pump control, then no, the MS300 doesn't support directly from its firmware the multi-pump control. You can, of course, program its built-in PLC, but I think you are actually referring to connect 6 motors at the same time. So I think you're not referring to the multi-pump control, but rather to controlling simultaneously 6 motors. So if you have, for instance, one big MS300 drive, and then you have some smaller, if you have like 1.1 kilowatt motors, 6 of them, and then you select one bigger drive, like one 7.5 kilowatt MS300 drive. If that is your question, then please let me know. Yes.
Yes,
So
it's
that
for
is your question.
conveyors.
That is possible, but there are some points which you need to be careful with, and I can list them down. So one is the total motor cable length. So you need to sum that up, and you need to make sure that you don't exceed the maximum allowable length. You also need to make sure that you size an output inductor. For this, normally you need that. You need to make sure that all the motors are identical. So you cannot select one motor which is bigger than the others. Another point is that you need to have thermal protection for each individual motor. So while the drive will still protect for short circuit, the drive cannot detect if only one of the motors is being overloaded. Since the drive is much bigger and has many other motors, it cannot really distinguish from a higher load on all motors, or when one single motor is being overloaded. So you need to make sure that you size thermal protection for each of your 6 motors. And I think there are some other points which you need to be careful with. But yeah, if you have an application like this, then you can send me all the details, and I can look into it, and I can let you know if that will work or not. Okay. So I hope this answers your question.
Yes,
Okay.
it is.
Okay, so next I'll just show you I'll just put in this table a very quick overview of the different drives which I've just shown. So I'll mark them in terms of performance and maximum power that they can go up to. So first we have the older generation of drives, EL and E, can go up to 22 kilowatt. We also have the C200 drives, which is made for high-speed applications, so it can go up to 2000 hertz. We have, in terms of complexity, we have the ED drive, which is made for elevator applications, and I think it's it's one of the few drives which has a single phase model for up to 3.7 kilowatt. So that's 230 volt for up to 3.7 kilowatt. Most single phase 200 volt models stop at 2.2 kilowatt, but this is one exception. Then we have the C2000, which is our most advanced drive to date. We also have the CP2000 for fans and pumps, then MS300. In the future, we will release the MH300 as well, which is also a compact drive, but will support encoders and will support running in closed loop, field-oriented control. Then we have the CFP drive, which is on the same level as the CP2000. And then finally the ME300. So next, I am going to talk a bit about how to size a drive. So which drive is right for which application. And so the first question which you should ask is which voltage is available? Do you have 400, you have 200 volt single phase, 200 volt three phase? Most commonly, you will have 400 volt three phase, or sometimes depending on your location, you might also see 690 volts. And most motors can be connected either in delta connection or in star connection. So most motors can be run on two different voltages. So for smaller power motors, the delta connection will mean that the motor can run at 200 volt or 230 volt, and in star connection, in Y connection, is 400 volt. For higher power motors, the delta connection is 400 volt and the star connection is 600 volt. And you can see here an example of such a motor. So you can have it, you can check this. So the triangle means 400 volt and the star means 690 volts. And then, of course, if you connect the motor for 400 volt, so that is this connection over here, then also the rated current will be higher. So in order to achieve the same power, 15 kilowatt. If you connect the motor for 690 volt, then this will be the rated current. So you select the drive based on the voltage of the motor. So firstly, you select the motor based on the available voltage in that area, and then you will select the drive based on the voltage of the motor. Sometimes your network supply will not be exactly 400 volt. It might be 380 volt, or it might be 460 or 480 volt. You can still select a 400 volt drive for that. So that's a typical question that I get. You can check the input range in our user manuals, and then you can see that all 400 volt models can work on a supply network anywhere from 380 volts to 480 volts. So I can just quickly show you that. So if you check the specifications of a typical drive, then you can see it here. So 400 volt models can run on three-phase networks anywhere from 380 volt to 480 volt. If you check the 200 volt models, then you can connect them anywhere from 200 volt to 240 volts. So I mentioned earlier that I will explain why it's important to size the drive based on rated current and not based on power. In this example, you can see that the rated speed of this motor is 1430 and it's rated at 50 hertz. So this means that this is a 4-pole motor. So in this case, if there is no particular overload requirement, then it's more or less okay to size also a 15 kilowatt drive. This is one example in which it's okay to size a drive based on power. But you can have other applications in which you have these high torque motors. Sometimes you can have 20 poles or 30 poles or something like that. So those motors will normally run at a much lower speed, but will develop a much higher torque. So when you will check the rated current of the motor, you will see that it's actually much higher than what you typically see on a 15 kilowatt drive. So in those cases, if you select solely based on power, then you might select a drive which is too small for that motor. So it is for this reason that we always say that it's much better to select based on current. Besides this, there are also numerous derating factors which you need to take into account. And that derating is always done based on current and not based on power. And I will show you those derating factors soon. So to recap, you select the motor based on the voltage of the location, then you select the drive based on the current and the voltage of the motor. You also have to check the overload requirements. Some applications require a very high overload, so in that case you need to check if the drive can do that. You also need to check which functions are required. So you need to make sure that the drive you select does support those functions. You might have to derate. So derating means that you select a drive of a higher rating than that of the motor. And some typical conditions when you might have to do this is when there is a very high overload requirement, or when there is a high temperature. So for instance, you can check here a typical derating graph for high temperature. So in this case, if the ambient temperature is 55 degrees, then you will have, depending on the drive that you select, you will have to derate by 90%. So that means you will have to check the rated current of the drive. So if the drive is rated at 20 amps, you have to derate by 10%. So that means you have to multiply 0.9 by 20, and that will give you 18 amps. So if 18 amps are not sufficient to run that motor, the motor that you wish to control, then you will have to choose a higher power model of drive. Another factor for derating is altitude. So that is altitude above sea level. Normally there is no derating needed up to 1000 meters, but if you plan to install the drive on a higher altitude, then that's also something you need to consider. And finally, you need to derate the drive based on carrier frequency. So as I mentioned before, some applications require really high output frequency. So spindle motors sometimes can go up to 1000 or 2000 hertz. If you use a motor which needs 800 hertz output frequency, then you need to select a carrier frequency which is at least 10 times higher. So if the output frequency is 800 hertz, then you will need to use at least 8 kilohertz carrier frequency. And if you use 8 kilohertz, that means you need to derate based on this graph. So you will have, again, to take the rated current of the drive and multiply it by the derating factor for 8 kilohertz. So that is, depending on the model, we'll have to derate by either 87% or 84%.
I have one comment about derating about higher altitude. Be aware that the motor maybe is also already derated for that higher altitude. In that case, you don't have to do it double. You need to know how much the motor is derated, and you have to take that current as a reference, the normal current of the application, and not the derated current.
Very good comment. Thank you, Martin. One other derating factor, which I've not mentioned here, is the situation in which you use a three-phase model on a single-phase supply. So if I go back to this graph, it's common to see drives which are 230 volt three-phase being connected to single phases. This is sometimes needed in applications which need some higher powers, like 5.5 kilowatt, connected to single phase 230 volt networks. And in those cases, you also need to check with us to check for the derating factor. Okay, so moving on, you also have to size the drive based on the required IP protection. You also need to check how many inputs and outputs are needed. If you find that the drive does not give you sufficient IOs, then we also have IO extension cards for the C family of drives, and also in the future for the MH. Then you need to check if the drive needs to communicate with other devices, and if it does, then you need to check which protocol is needed. And finally, you need to check what is the required EMC and also THD. Here you can have different levels. You can have levels for domestic environments and also for industrial environments. But also you might have requirements in terms of total harmonic distortions. Some of our drives come with a built-in DC choke, and that lowers the harmonic distortions of the drive to somewhere below 48%. So that's in order to meet the EN 61000-3-12 standard. Okay, so are there any questions so far? And if there are no questions, then I will move on to the bench demo, and I can share with you the configuration that I have with me. Hopefully everyone can see my screen. So I have here an MS300 drive, which I'm connecting to with directly via USB. And keep in mind that this USB, if it's connected to your laptop, then it can also power the control board. So that means that you can program the MS300 directly from your laptop, even if the MS drive is not powered on, even if it's not connected to the main supply. I'm also connecting my laptop to this switch, which is connected to an AS200 drive, which is somewhere behind. And then from that from the switch, I'm also going into a daisy chain connection from the switch to the dual port Ethernet IP card. And from this Ethernet IP card, I'm then going into this dual port Ethernet IP card on this slave, on this follower C2000 drive. And then from it, I'm going into a single port Ethernet IP card, which is connected to another C2000 drive. So this is the configuration that I have with me. Firstly, I am going to show you how to connect to the MS300 via USB by using the new Dia Studio. So I have Dia Designer, which can be used to program and to monitor drives. So as soon as you open Dia Designer, you see this menu. You can go directly to Inverter Wizard. And one thing which I should mention, especially useful if somebody else has been working with the drive that you are about to work on, it's very important that you first actually reset the drive to default. And you can do that by setting parameter 00.02 to 9. And you can see that I got an error message. And the reason for that is because you cannot reset the drive to default if the onboard PLC is enabled. So firstly, you have to disable the onboard PLC. So I'll do that by pressing mode a couple of times until I get to this screen, PLC 1. So PLC 1 means that the onboard PLC is enabled and is in run mode. So I will just set this to 0 and press enter. So now I will go back again to parameter 00.02 and I will set this to 9. So 9 means that the drive is reset to its 50 Hertz default. Okay. So now that I know that there's no strange setting on the drive, I can start my own test. So going back to Dia Designer, firstly you get brought to this screen. So if you click on Inverter Wizard, you can select the communication address. This is the default setting for your address. So I can click on Start Detect. And you can see it here. That's successful. And then I can just click to add this drive to my network. So firstly, I have this drive. So Dia Studio, Dia Designer correctly detected the drive type that I have. First off, you have here communication settings. And I want to also connect the onboard PLC of the drive. So I double click on communication settings. Firstly, I disconnect. And I tick here, enable built-in PLC communication. Then I will click connect. And you can see here that it's failed to connect to the PLC. The reason is because I need to re-enable the onboard PLC back. So I've not done that. So I can click on mode a couple of times. Then I'll set it to PLC 1, which is PLC run. Press enter. So now you can also see a tiny dot here where it says PLC. This dot tells you that the onboard PLC is enabled. So now I'll try again. Firstly, I'll disconnect. I click on enable built-in PLC and you can see here I'm successfully connected to the PLC. So I will close this. Next off, you can see the different error information and the previous fault codes. For hardware configuration, you can check the parameter settings in this screen. So now you can just upload everything from the drive to your PC. But since since default values, then there's not much to upload. So I just upload everything, but you can also upload parameters one by one. Then you don't have to wait so long. And so everything was successful. I want to control the drive firstly from the designer. So because I'm connected with Modbus with RS485, I need to set parameter 0020 and 0021, which is the source of control for frequency and source of start-stop. I need to set them to RS485. Then you can check this in the user manual. You can see the right settings are for RS485, 0020 needs to be set to 1 and 0021 needs to be set to 2. So I will do that. Set this here, 1, set this here, 2. You can also see that this is now different from its default value, and I can click on download and download. Okay. So yeah, you can also program all the different parameters, and then you can also save the parameter settings and upload other parameter settings, and you can even convert your VFDsoft parameter files to a DIA Designer format. So next I will go to the commissioning page. You have here trace. So this is the new oscilloscope function. So I can just drag this out and I can make it a bit bigger. So I can click here to start monitoring. And then I have here the options to start and stop. You can see that, yeah, there is a different scale for each of the 4 channels here. So if if I click run, then should see the drive starting. Yeah. I can also change the frequency command from here, so I can just set it to 15 Hertz, and you can see the frequency command decreasing here. And then on the blue line, you can see the actual output frequency. Now, since these are not all on the same scale, then yeah, you don't really see them that well. So I just stop, and I can just tick here so that we only have one coordinate. And this is more to what I'm familiar with. Maybe you also prefer this, but I guess it really depends on the individual engineer. Some maybe prefer to see it more like this, but yeah. Normally, I would prefer to just scale down the DC bus voltage. So you have here a gain setting. So I would just set this to 0.1, and then it's more or less in the same range with the other values. And then you can zoom in, and then you can see what's happening. And yeah, for the current, it may be a bit too small, so I can also set this to a factor of 10. And then it's more easy to see the different values. And if you want to monitor to measure, for instance, the distance between different points, then you can click here if you want to measure the time between so I want, for instance, to see how long it took the drive to reach from 0 Hertz to 47 Hertz. So I can just set these here. Yeah, and you can then read the time in this area here. So you can see it took 9.9 seconds to reach that speed, which more or less corresponds to the acceleration ramp, which you can see here. If you want to measure for amplitude, then you can also do it with these lines. So if you want to see the difference between the 2 lines, then you can check it here in the delta Y. Or if you want, you can just check the absolute value over here. So 48, 49 something. I will show you one function that you might be familiar with from VFTsoft, which is to test the communication, the Modbus communication. So we still have that in DIA Designer. So if you are not sure if your Modbus communication or if some register is being read correctly or written into, then you can just check this tool. So for instance, I can check the status word, which is 2101. You can write it here. And then this is the value that that you get. You can also see it in binary so that you know each bit, what it does. And then I can also check, for instance, the DC bus voltage in 2104. No, I think that's in 3. Or better yet, I can just check the user manual and not guess. So you can find the complete list in chapter 12, menu 9. Which is over here. Yeah, so the DC bus voltage is in 2105. So 2105. Yeah, and I can see it here. The DC bus voltage normally has 1 decimal point, but you don't get the decimal point here. So then you just read it as 3083, but that's actually 308 volts, which is more or less what you can also see here. Okay, you can also give the drive a frequency command, but I think you more or less understand the idea of this, so I'm not going to go into too much details here. So if you don't have any questions on this, then I will move on to programming the onboard PLC of the drive, so which you can see over here, so the PLC function. So what I will do, so I expand this part and I will create a new program, which is over here. So I will click on add program, new one. And you can see all the different PLC functions in the user manual. You have it here in chapter 16, PLC function. So first, what I'll do, so it walks you through the different connection possibilities and also the different IOs that you can access. You have here X and Y's. And first thing is I'll go to the special M functions. So over here. So I will create a new contact. I can set this either to a physical input or just one from the onboard PLC. So I won't use a physical input this time. I just set, for instance, M1. And then I will set this to M1040, which is power on. You can also see it here. So hardware power. And I also have to use this one, M1025. So I'll put a new contact, M2. Now I can enable the drive from the onboard PLC. I also have to be able to set a frequency command on it. So I will add a new line. I'll set this as M3. And then I will add a new frequency command. So that's FREQ. Can have here the complete description of the function block. So you can see S1, which is here, S1 will be the target frequency, then S2 acceleration and S3 deceleration time. I won't set these as constants. I want to be able to modify them while I am online in the program. So I'll set these as D registers. So D1, D2, and D3.
Small question in between, Vladimir.
Yeah.
Is it also possible to program the onboard PLC with Ethernet, via Ethernet, or not?
Not at this time. That's something we have been pushing to support, and also to program not only the PLC in the drive, but also the parameters. So that's something which we will support in the future, but not at this moment.
Okay, thank you.
So anyway, I will now compile this. So there's no error. I can download this from PC to device. I can see this was successful. Okay, so now I can go online. I'll only go online with the onboard PLC. So I can see I already have some values, because when I reset the drive to default, I did not reset the onboard PLC as well. So then I still have the older D1, D2, and D3 values here. Otherwise, they would have been set to 0. So I can set this to true. And now I can see that the drive is enabled. And now when I set this one to true as well, then I can see the drive running. I can either share my screen to show you the motor running, but I think it's more interesting if I just also monitor from here. Yeah, and I will go offline here. And I will just use individual coordinates. That's better, I find. So I'm now online. I can change this to 20 Hertz. So I set here 2000. And then you can see it here. I can change the deceleration ramp to be much slower. So I can set it to 10. And can give it yeah, so now it's okay. Can give it a frequency command of 10 Hertz. And so, yeah, if you have the user manual and you have access to all of the special M and special D registers, and you also have access to the different functions which are explained here, then you can build upon this and you can create some very complex programs within the limit of the drive, which is 10,000 steps. So I won't go further with this. This is just a very basic introduction. So if you have no questions on this, what I'll do next is I will show you the C2000. I will present the positioning function on the C2000 via Ethernet. You can see it here. In my configuration here, I have two C2000 drives. So they're both connected via Ethernet. I also have PG card on each of these drives. So both drives are running in field-oriented control, PG, so that's closed loop. And both of them are running a PM motor. Now, all PG cards have have different terminals. So you have firstly PG1 for connecting the motor. You have PG2 for connecting an external source of pulses. And then you have PG out, where you can get pulses out to another drive. So if this drive were configured as a master, then you could take the pulses which are coming in from this motor, and you could output them on these terminals. And you also can see here. So in this configuration, I have this drive running as a master, and this drive is configured as a follower. So you can see here the different terminals which I just mentioned. And also you can see here how they are wired. Now, I'm not going to go into too much detail regarding the position synchronization because we already have a YouTube video on that. And we also have an application note on that. But yeah, it's very easy to do. So how to do this synchronization, how to program the slave master, I'm not going to show you. What I will show you is how to program this drive in positioning via Ethernet. So I'm going to connect to the AS200 PLC, which is connected here, and then going into a daisy chain all the way here. And if you want to know how to synchronize the drives, then you can check out our video on YouTube in which we show how this is done. And you can also check our application note in which we show you how to do this. Okay, so firstly, you need COM Manager. I have COM Manager version 2. This is the version for Dia Studio, but you can also use COM Manager version 1. Firstly, I will just delete this. Initially, what you might want to use is DCI Soft. So this is a software to configure your Ethernet network. You can, of course, program the IP addresses on all of your drives directly from the keypad. That's okay, I guess, if you have 1 or 2 drives. After you configure the IP address, there is one parameter which you need to set in order to save that. But if you have many devices connected on your network, then it's much more convenient to just use DCI Soft. That is this software here. So you can just click on this tool, and then that immediately detects all my cards. If they were the same type, then they would all appear on the same row, but I'm using different types on all drives. And I'm going to run this drive, which is connected to this card. So you can check here the address, which is set to it already 192.168.110. And if you want, you can also change this address from here. I'm not going to do that. I'm just going to go directly to COM Manager. And I will select Ethernet. Just click on Search. Now, the dual port Ethernet IP cards are not yet supported by Dia Studio, so that's why they appear here as unknown. That's going to be supported very soon. So I'll just save this, close it, and I will open ISP Soft. So here I need to firstly set the driver which I saved in COM Manager. And I have here all the different IP addresses, but I need to connect to the one from the AS200 PLC. And I can click here on PLC and click on System Information to make sure that I've connected properly. Yes, since I get the screen, then I know that I have a good connection. So I see here AS228T. I will create a new project with this PLC, AS228T. Firstly, I'll go to hardware configuration. So this opens up a new screen, which pops up here. I can right click on the PLC, then communication software and Ethernet IP. and I'll just scan my network. So and I can connect everything. So I'll press OK, and I can just click on Fast Connect so that I get everything all in one. So now all my drives are on the same network, and this is the drive which I will control in positioning. So what I can do is I can right click on the PLC and then click on Data Exchange. I will first go here. I will put all the read information on D0, and so that will start from D0, and I'll write from D100. So I'm very generous with the space that I get here because I know there is quite a lot. So put the second one, D200. So in the real application, you might not have the luxury to do this. And if you double click, then you can select here the read addresses. If you have anything which you would like to read, like any parameter or any specific register which isn't in the predefined ones, then you can select it from here. There's nothing in particular that I would like to see. Well, maybe the motor position. So I can do that from here if I map out 222C, and then I'll also map out 222D, because the motor position is a 32-bit register. Then I have it in two of these 16-bit. So now I can read also the motor position. And I'll click OK. And then this is where I can write into, and I will use the 6000 registers. So starting from here, you have a parameter in the drive in which you can select whether or not the drive should use the 2000 registers or the 6000. But if you want to control the drive in positioning, then you can only use the 6000 registers. I'll make a print screen of this because I need to refer to it later on. So take this. So I have it saved here. Click OK and OK. So now I know for this drive I'll read in starting with D0 and write starting with D100. So I'll close this. I will download this data exchange. Close, and then I will also save. Okay, so I will close this. And I will create a new device monitor. So you can do this. Click new monitor table. So I will start from D0. And I will read for around 32 parameters. Okay, and then I will write from D100 for around, I don't know, I think 10 or so. Okay, so I can compile all of this. I need to create an empty project first, otherwise I cannot compile. Yeah, so I can compile. I can now download. And now I can go online, and I can read all the 6100 registers. If you want to see what what's the description of all of these, then you can have a look at the at the 6000 100 descriptions. So firstly, you have 6100, which is the status word, and this is 0. You have the different registers. This is 2000 and then 2001. So I can go back to the hardware configuration, which is, so I can go back to the data exchange. So yeah, that's why I always say it's important to take a print screen to have some idea of what you are actually reading. So okay, so I'll go back to ISPsoft. So what I'm actually seeing here is 2100 all the way down to the to 26 and 27. So that should be 25, 26, where I can see the motor position. Yes, and you can see it here. If I move the motor by hand, then you should also see this change a bit. Yeah. And this is also the position which you can also see on the drive itself. The second camera, then you should also be able to see it here, 9010. Okay, so currently I think the drive is set to run in speed mode, so I can just initially set a speed command. So I can do that if I check the register. So currently the drive is set to run from the 6000 addresses. So that is from, this will be from 104. So that will be here. This will be the status word. And I can check which bits I need to enable by checking here. So 6000. And then I need to enable bit 7 for servo on. And then bit 0 to actually run. And I can set the frequency command in 6002. Then I can change the position, the operating mode from speed to position in 6001. So moving back here, I have here the 6000 address. I can change this. If I enable bit 7, then I can see the drive being enabled. Okay. But I can also see that the speed command is 0. So even if I give it a run command, it's not going to go anywhere until I give it a speed command in 6002, which is mapped here in D106. So I'll just give it a speed command of 1, 2, 3, 4. So that's 12.34 hertz. Yeah, and then you can see the drive running at the frequency command which I just gave it. So you can read it here, 34. Can also change this. And then I can give it a stop command. Okay, so I have verified that the drive is working properly in speed mode, which is something that you should always do before changing to positioning mode. So now that I know this works well, I'm ready to move the drive to positioning mode. So one of the first things which you need to do is you need to make sure that the drive positioning is set from the source which you need it to be. So you can do the positioning from digital inputs. You can also do it from external registers. So for example, the follower drive. So for example, this drive is set to run from external pulses. So that's 1140. You can see here, it's set to run from external pulses, which is from here. For this drive, I will set it to run from Ethernet. So I will set 1140 to run from communication card. So at the moment it's set to run from digital inputs. I can also run the positioning from the onboard PLC. That's something I'm not sure if you also want to see that, but that's something which I can show you later on if you're interested. So I'm just going to set it to run from the communication card. So another thing which I have to do right now is to set also 6001. So that is this address. I need to set this from 0 to 1 to position mode. So 6001. That will be in D105. I'll set this to 1. Okay. So I will, I'll give a run command firstly. So servo on, and I can see the frequency is set to 0. And for positioning mode, if I enable this, this will be the command to move to a new position. But if I enable this, then nothing happens because I've not given it any position command. So you can check again this definition of 6000. You can see you have in 6004 and 6005, you have the position command. So that is 4 and 5. That means target position will be in D8 and D9. You can also set it here as a so if I give it a command of 10,000 in relative mode, then that will mean that the drive will perform exactly 1 turn. And the reason for that is because the drive currently has an encoder which is 2,500 pulses per revolution. That means that within 1 revolution, the drive will count 10,000. So that's 4 times that because it's an ABZ encoder. So for each rising edge and for each falling edge, the drive will count once. So this 2,500 pulses per revolution encoder gives 10,000 counts per revolution. So when I give it a command of 10,000, then the drive should move exactly by 1 turn, which it does. And you can also see that when I share my screen here. So I set bit 0 to off, and now I set it on again, and there you have it. This is currently set for relative positioning. I can also set it to do absolute positioning, but for that, first we need to do a homing. So in order to do a homing, firstly, I need to disable this. So in order to do the homing, firstly, you need to check which homing method you want to use. So you can do that in parameter 1168. So currently, this follows the DS402 standard. So homing number 8 means that the drive will just set the current position as the home position. But you can also do the homing based on negative limit, positive limit, or origin. I will just leave this at its current value at the moment. And yeah, I can also program one digital input to be to start the homing. So for instance, MI1, if I set this to 47, then this enables homing. So when I trigger this, when I trigger MI1, you should see the position of the drive switch back to 0. So firstly, I'm going to give it a servo on. And then I have a digital input over here. Yeah, and you can see the position switching to 0. Okay. So now I can go back and I can show you the different options that you have for homing and for positioning. So for homing, you have quite a lot of options. And then if you want to do the absolute positioning, then that will be similar to the relative positioning. You just need to enable bit 2 of register 6000. At the moment, bit 2 is set to 0, so that means relative positioning. I will enable it, and now when I give it a run command, then it goes exactly to position 10,000. And you can read this here in registers D25 and D26. Yeah. If I give it another run, then it's not going to run because it's only going to do it if it's in relative positioning. So when it's in relative positioning, it's going to go every time. But if I set it back to absolute positioning, then it's going to go 2 rotations back from 30,000 back to 10,000. Okay. I can also give it a higher position command. So I can set here a 32-bit value and then. So this will be 12 rotations. Okay. And you can see here the 32-bit value, which I've just written. And that's about it. You have different parameters where you can set the maximum point-to-point frequency, where you can set also the acceleration and deceleration. And all of these parameters you can find in our documentation. So I hope this was useful to you. If you have any questions, then please let me know. And if not, we will conclude our presentation for today. So since there are no other questions, then thank you so much for joining today, and send us any questions that you have on IA technical support. So thanks again and have a nice afternoon.